So how do you convert Kp and Kc? Well, you can derive by substituting in into the ideal gas equation, essentially PV equals nRT. If you rearrange that so you get N over V, which is number of moles per volume in liters, that is concentration, molarity, right? So you can find a relationship between pressure and molarity, and the difference is RT, right? The gas constant times the temperature. You can put that into an equilibrium constant expression, and you come up with this relationship that Kp is equal to Kc times RT, and then that will be to the power of the difference in the number of moles between each side of the balanced chemical equation. So that's going to be delta N. So how we calculate delta N, if we take our generic expression for any kind of equilibrium reaction of A moles of reactant A plus B moles of reactant B, forming C moles of C and D moles of D, delta N is going to be the difference in terms of number of moles of product C and product D minus the number of moles of reactant A and reactant B. So that will give you your delta N. So you've got to look at the number of moles of all your reactants and products, obviously, only if they appear in your equilibrium constant expression, right? So in this particular case, how many moles of products do we have? We've got 2 moles of nitrogen and 6 moles of hydrogen. So it's 8 moles of products. And then on the left-hand side, we've got 4 moles of ammonia and 3 moles of oxygen. So that's 7 moles of reactants. So now we don't actually have to solve for this. It's just asking us for an algebraic expression. We know what delta N is going to be. So delta N is going to be C plus D. So that's going to be 8 moles minus A plus B, which is 7 moles. 8 minus 7 is just going to be 1. So delta N is going to be 1 in this case. So now we can substitute delta N equals 1 into my Kp expression. So Kp is Kc times RT to the power of 1, which is just Kc times RT. So that's all you're going to do for this kind of question. Basically, the power of RT is going to change depending on your composition in terms of relative number of moles of products and reactants that appear in the equilibrium. I'll do a little follow-up example, just in case you guys are a little bit not sure what happens if we have like a negative power or something. So if we look at this particular example, we have 4 moles on the reactant side, and we have 2 moles on the product side. If I could spell product, that'd be nice. Okay, so in this case, when we do delta N, remember you always do products minus reactants, initial minus final. So we do 2 minus 4, and we get an answer of -2. That is totally okay. We can still use our expression for Kp. So Kp is going to be Kc times RT, and that'll be to the power of -2. Okay, so algebraically, that is all we have to do. We just have to stick it to the power of -2.